In the next part of the section, we will talk about piecewise functions. A piecewise function is a function where more than one formula is used to define the output. Each formula has its own domain, and the domain of the function is a union of all these smaller domains. So I think the best example of a piecewise function in real life are tax brackets. If you're unfamiliar with our tax system, your tax percentages are based on a formula which is based on your income. So those people that have a higher income should pay in a higher tax bracket compared to those who have a lower income. It doesn't always work like that, but that's how it should be. So here's an example. We're given the piecewise function f of x equals to 2x minus 1 if the values of x, our domain, is less than 3, and 5x squared plus 9x minus 3 if our values of x, or our domain, is greater than or equal to 3. Now here's the easiest way, in my opinion, to set this problem up. I'm going to make a number line, and I'm going to split up the number line based on our domains. So our first function, 2x minus 1, is used when our domain or x values are less than 3. So I'm going to indicate that on my number line. So here's 3, and I have an open circle or a parentheses on 3, and anything to the left of 3, so anytime x is less than 3, I'm going to use 2x minus 1 to find my output. Now, if x is greater than or equal to 3, we're going to use 5x squared plus 9x minus 3 in order to find the output. So let me indicate that on the number line. So greater than or equal to, this means I'm going to have a bracket, and when x is greater than or equal to 3, I'm going to use the function 5x squared plus 9x minus 3. Setting the number line up this way, it is very helpful, because when we start evaluating the function at various inputs or x values, we can clearly see based on the number line which function to use. So let's start with the first one. We want to find f of 0, which means we want to find the value of the function, the output, when x equals to 0. And we learned in the previous section that the parentheses always contains our input. So in the first case, our input, or our x value, is equal to 0. Now we have to determine, for x equals to 0, which function do we use? Do we use 2x minus 1, or do we use 5x squared plus 9x minus 3? So let me plot x equals to 0 on my number line. This is 3, this is 2, this is 1, this is 0. X equals to 0 is this point. Now, x equals to 0 is less than 3, and we can see that on the number line. So for x equals to 0, we would use the function 2x minus 1 to evaluate the output. So instead of 2 times x minus 1, we know that my input is 0. So I have 2 times 0 minus 1. That's 0 minus 1, which is negative 1. So for proper notation, I'm going to write that f of 0, in other words, the value of the function f when our input, our x, is 0, is equal to negative 1. And the reason we use 2x minus 1 to evaluate the output is because 0 falls in the domain where x is less than 3. And we can also see that on the number line. Let's take a look at our next example. We want to evaluate f of 4. So in this case, our input is equal to 4. And once again, the parentheses contains our input. So let's locate x equals 4 on our number line. X equals 4 is going to be right there. Now, which domain does it fall in? It falls in the second domain, where x's are greater than or equal to 3. So when x's are greater than or equal to 3, we're going to use 5x squared plus 9x minus 3. And if you set up the number line, we can see that it's in the green section, for which we're going to use 5x squared plus 9x minus 3 to evaluate the output. So we have f of 4 equals to 5 times x squared, which is 4 squared, plus 9 times x, which is once again 4, minus 3. So each of the x's are being replaced with the input, which is 4. In the order of operations, we would first evaluate the exponent, which 4 squared is 16. So we have 5 times 16 plus 9 times 4 minus 3. 5 times 16 is equal to 80. 9 times 4 is equal to 36. And you have minus 3. If you put this all in a calculator, we're going to get 113 as the answer. So for proper notation, we would say that f of 4, in other words, the value of the function f when x equals to 4 is equal to 113. Let's take a look at our next example, f of negative 1. We want to evaluate the function when x equals to negative 1. Let's find negative 1 on the number line. Negative 1 is here. And we can see that in this region, we're using the blue function, which is 2x minus 1. In other words, whenever x is less than negative 3, whenever x has a value of less than 3, which is negative 1, we're going to use 2x minus 1 to find the output. So f of negative 1 equals to 2 times x, which is negative 1, minus 1. So 2 times negative 1 is negative 2, and negative 2 minus 1 is negative 3. For proper notation, we're going to write f of negative 1. In other words, the value of the function f when the input is negative 1 is equal to negative 3. Lastly, let's find x equals 3. Now 3 is a boundary point, because when x is less than 3, we use 2x minus 1. When x is greater than or equal to 3, we use 5x squared plus 9x minus 3. So which function do we use when x is exactly equal to 3? Well, the first function, 2x minus 1, is used when x is strictly less than 3. So if x was 2.9 or 2.8 or anything that's strictly less than 3. But if x was greater than or equal to 3, we would use the green function, 5x squared plus 9x minus 3. And we can see that with the bracket on 3. So when x is exactly equal to 3, we are going to use the green function, which is equal to 5 times x squared plus 9 times x minus 3. To evaluate this, we do the exponent first. 3 squared is 9. Then you got 9 times 3 minus 3. Remember that in order of operations, only one step at a time. Now we can do our multiplication. 5 times 9 is 45. 9 times 3 is 27. And you have minus 3. And if we add this, this should give you 69 as the answer. So we're going to say that f of 3 is equal to 69 for proper notation. The next example we will go over in class. So think about the example. You can try it out if you want to. More importantly, think of questions you have, and we will go over this in class.